All right, so we're looking at the solutions introduction worksheet, and the first question is to explain why solutions are mixtures instead of compounds. So this kind of goes back to that picture we were looking at the other day, where we were trying to decide if it was a mixture or a compound. So we had those boxes, and we had the circles, and some of them were colored in, and some of them were not, and we can insert one where there's a mixture of colored in and not colored in joined together. Okay? So if we look at just a single one of those, like this for example, that would be called a would it be a compound or a mixture, just one of these?
Compound.
Okay, and why is it called a compound?
Because it's
Okay, so it's two or more types of elements, and it's uniquely compound because they are bonded together. All right, but when we put a bunch of those things in the container and they don't get bonded together, that's called a mixture. So in a mixture, things that are classified as mixtures do not contain bonds, while things that are compounds are bonded together. So in a mixture, you can have compounds, but the whole thing itself is not bonded together. Okay? So to have a mixture, though, you have to have two different kinds. So if we had a box with just water compounds in it, the same type of compound all the way through, that would not be a mixture. But when we get a container with some water and some sodium chloride, that would be a mixture. Okay? So compounds are bonded together, mixtures are not. All right, solutions are what kind of mixture? You have one? Homogeneous mixtures made of very small particles that are actually molecules. Okay, so what we mean by molecules there is covalent compound. Molecules or got ions on here, really for atoms. Okay, because all of these are types of particles. So we wouldn't want to use the word particle there because we were saying or. So we can have molecules, atoms, or ions. So just to clarify here, molecule would be covalent, atom would be just one thing by itself, and then ion would come from ionic compounds. So any of those can be together in a solution, but it's homogeneous, meaning same throughout. All right, good. Solutions are said to be in a all right, so they can be in any phase, solid, liquid, or gas, but they're said to be in a single phase. A single phase. Even though some components may be in a different phase before the solution was formed. So for example, carbonated beverage is a gas inside a liquid, but as a solution, it's considered to be in one phase, the liquid phase. Okay. Pure gold is 24 karat. 14 karat gold contains 14 parts gold and 10 parts other metals. 14 karat gold is said to be a perfect alloy, which is a type of good. Stop. An example of a gaseous solution is air, which is made of mostly, okay, I'm just going to put O2, and nitrogen. The most common solutions, however, are liquid. So we do have metal or solid solutions, and we do have gas solutions, but most commonly we're making liquid solutions. So as we go forward here, we'll be talking mainly about those liquid solutions. All right? Define miscible and immiscible. So these are just opposite words. So miscible is when two substances mix or dissolve in one another to make one homogeneous solution. All right, Immiscible is the opposite. I'm not going to write out that whole definition, but you can kind of figure, okay, whatever the opposite of that is, it would be two substances that do not mix or dissolve to make one homogeneous solution. So what type of solution are we going to get when we have immiscible things? Heterogeneous solution. All right. I have that repeating, so we'll go down to number 7. All right. What effect causes us to see the light beams from car headlights in fog? You get that one? Tyndall. Okay. Tyndall, I believe. Tyndall. Okay. All right. Do you know what type of solutions the Tyndall effect applies to? It is a type of hetero. It starts with a C. Oh. Colloid. Okay. Colloids undergo the Tyndall effect. So milk is an example of a colloid. It's hard to see the Tyndall effect very often because most of our colloids, we can't see light going through them anyways. Okay, but if they catch light, that's a colloid. Okay, but again, milk, you wouldn't be able to see the light going through, so it's hard to say it's catching it. But the fog, we can see light coming through the air, and then when it's foggy, we see the fog catching that light. So the Tyndall effect. All right. Rate of solution is next. So to increase the rate of a solid, so it's important to make a distinction of what we're dissolving because it's different for a gas. But to increase the rate of a solid, would we increase or decrease the pressure? Should have no effect. So pressure is about when you're dealing with a gas in water. And if you do have a gas in water, you want to increase the pressure to push the gas down into the water. Okay? For example, when you take the lid off your Coke, the gas comes out. You decrease the pressure. You want to increase the pressure to keep the gas in. Would you crush the particles of a solid to help it dissolve faster? Yes. Okay? So C. And chilling the water would cause that to slow. Again, it's opposite for a gas.
Daniel, please come to the front office. Anthony Daniel.
Opposite for a gas. Okay. If 15 grams of iodine are dissolved in 1,000 milliliters of alcohol, the alcohol is the the one in the larger portion is the solvent, and the solution is said to be tincture. Yeah. Okay, and that's the word we use when something is dissolved in an alcohol or when alcohol is the solvent. If alcohol is the solvent, that's the vocabulary word there. If water is the solvent, it's called, comes from the word aqua. Aqueous. Good. All right. A substance that dissolves another material is called the one that's doing the dissolving. The substance that dissolves is called the solvent, and the substance being dissolved is a okay. So they mix up the wording on us a little bit there, so just be careful to read those problems carefully, especially on multiple choice tests. The one that's doing the dissolving is the solvent. All right. In blank, the substances separate after standing a while. In a suspension. You can think of that word. That means those things are suspended. Okay? And so they're going to fall down. The substance can or cannot be separated by filtration. Can. Okay? In a suspension. But in a solution, in a real solution, they cannot. So a suspension is a heterogeneous, just like a colloid. So hetero can be separated by filtration. If it's a true solution, it should not be separated by filtration. So if you have a saltwater solution, for example, you can't filter the salt out. All right. Smoke is an example of a suspension, okay, of solid dirt and dust particles in air. After a while, the solid particles will fall to the ground. So the key here is falling out. That is a suspension. In a blank, particles are between those of a solution and a suspension. Column. Okay. So, in the same way as a suspension, they're heterogeneous and they're suspended, but unlike a suspension, they're not going to fall out. They're too light. Okay, they're kind of trapped. Right? Blank are actually colloids of one liquid in another liquid. Emulsion. There's lots of vocabulary in this worksheet. A blank agent keeps the particles mixed. Emulsifying. Okay. Emulsifying agent keeps the particles mixed. All right. What is an aqueous solution? So keyword there, aqua. So that's a solution where good. Something is dissolved in water. The key is that water is the what? Solvent. Good. Water is the solvent. Okay. This is the opposite, or not the opposite, but related to that tincture where alcohol is the solvent. All right. What is the solute if we have 75% copper and 25% zinc? Okay, the one in the smaller amount is the solute, and the one in the larger amount is the solvent. So the zinc would be the solute. Okay, this is smaller concentration zinc, not zinc. All right, how does a solution behave differently from a suspension when a beam of light is shined through it?
Anthony Daniel, please report to the front office. Anthony Daniel.
All right, so in a solution, it's even throughout. So what did you say light is what?
Evenly shown through and absorbed.
Okay, so light, keeps wanting to click incorrect. All right, so we're going to say light passes through evenly in the solution, but in a suspension, the light would be scattered. Okay? Scattered. Right? And the reason is because in a solution, because we're homogeneous, we have uniform particle size throughout. But in a suspension, we have varying particle size. So we'll have these big particles and small particles that will catch light differently and therefore scatter it, which is somewhat similar to the Tyndall effect. Okay? But it happens in any suspension. All right? And then lastly, substances that conduct electricity when dissolved are said to be electrolyte, while substances that do not, very simply, are non-electrolyte. All right, so if you're listening from home, a quick note, do not write exactly what I wrote, but put things in your own words where appropriate.